The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thank you. Just by a quick show of hands, who's read the accompanying paper to this presentation? Literally, one, great. Well, for the rest of you, you're in luck. Consider this the Cliff's Notes version of that presentation. So just a quick chance to acknowledge my colleague who helped with this presentation as well as the paper. Tom Vickers is certainly an expert in the industry. Today's presentation will focus on two things. One, how modifications to PCE molecules still allow for new performance space, and two, how that performance space impacts producers beyond just the performance in concrete. PCEs have been commercially available in the market about as long as I've been alive. And since then, scientists have been manipulating three key features of the polymers to create new performance space. Those three key features are your main chain, which is the vertical black line, your side chain, those blue squiggly lines, and your charge centers or bonding sites in the green circles on that diagram. And in the next few slides, we'll talk about the results of laboratory experiments that have taken these modifications and demonstrated how, one, we are still able to produce commercially viable improvements to such a long-standing technology and how that technology translates beyond the concrete performance. We'll demonstrate the faster cement dispersion capabilities as well as a reduction in sensitivity to changes in cement composition. For the experiment, we utilized two cements, one being a high alkali cement and the other extreme being a low alkali cement, as well as those cements in combination of two mix designs. Those mix designs are listed over on the chart on the right. And they were chosen with the intent to demonstrate the influence of polymer modifications in more difficult to wet out mixes. So we wanted to push the extremes and really start to identify how the purposeful manipulations do in fact impact these designs. We looked at how do these PCEs perform as a function of both the cement chemistry and the dispersant polymer characteristics. A constant paste volume was chosen to maintain a better comparability between those two mix designs. It's important to note that from here on out, in terms of the cement dispersants, PCE1 is our newer generation faster dispersing technology, and that will be compared directly to the PCE2, which is your more general purpose polymer that's readily available today in the marketplace. Here we have the actual laboratory results starting with our high alkali cement. The blue line represents the performance of our PCE1, which is again that faster dispersion technology. The red line demonstrates the performance of our general use polymer. And on your axes you can see we're measuring essentially workability, so slump flow and diameters. Along the bottom is time. And this is the mix design one, so it's a straight cement mix. You can see that the faster dispersion is very obvious in this design. It achieves its ultimate workability within 1 minute of our standard mixing time, while it takes upwards and beyond 2 minutes for your traditional PCE to achieve that same level of workability. Additionally, if you look on the bottom, the dosage rates, and these are dosage rates active polymer by cement, you can see that the PCE1 not only has faster dispersion capabilities, but it also requires less of an active polymer to achieve the same level of workability. Those trends are directionally the same with our second mix design. Again, this is in high alkali cement. You can see the blue line represents, again, the performance of the faster dispersion technology versus the red line, the general use polymer characteristics. Again, directionally, you can see that the workability is achieved faster with the faster dispersion, more around that 2-minute mark, versus, again, 3 minutes and beyond in the general use polymer. The dosages continue to be less required by that faster dispersion polymer to achieve your ultimate workability versus the general purpose PCE. These results were directionally the same when we switched cements. These charts are the exact same that you had seen on the previous slide, except for we changed the cement. We are using a lower alkali cement, so everything is shifted, but the experiments are the same in terms of their results. Again, in a straight cement mix, we see that blue line achieves its ultimate workability within a minute of mixing, while the slower dispersing general use polymer, that red line, achieves its ultimate workability by 2 minutes. When you move to our second mix design to compare the results, again, we're achieving ultimate workability within a minute of our mixing with our faster dispersion PCE1 versus our general use polymer, that red line that achieves its ultimate workability at 2 minutes. When you compare those again directionally, while it's not exact comparisons, directionally we're still requiring less of our faster dispersing PCE to achieve that same level of ultimate workability in both scenarios. And again, across both types of mix designs and across those changes in cement dictated by the alkali contents. You can make the leap, it's not such a huge leap to make, to say that not only do you see consistent faster dispersion with lower dosage, but you see magnitude less change in your dosage required across the two cements. So faster dispersion and less sensitivity to changes in cement. Where this starts to really impact down the value chain in terms of how do you take this technology, there are clearly benefits to the actual concrete performance, but there's also benefits beyond that, and those are coming in the form of operational efficiencies to a producer. So how do you quantify this? How do you know you have operational efficiencies? And the key is exactly what I said. You have to quantify it. So you have to put yourself into the shoes of a producer, if you're not already one of them, and think about, what does faster workability mean to me, and how can I benefit from having less changes in terms of my dosage and performance when I have different types of cements in my system, or in my yard, or in my silo, or my supplier changes. We built a tool that helps you really start to quantify this, and the nice thing about this is that it's using actual data. This up here is a fictitious example just to demonstrate the types of information that you're looking for and how you start to quantify this for your operations. All of the red information is input. So you have to first, you take your existing operation and you run it with your general use polycarboxylate, whatever product you're using, and you establish your baseline. In terms of faster dispersion, that really impacts two portions of any type of batching process. That is the mixed concrete time. How long does it take your mix to come together? How long does it take your batch plant? Or if you're a central mix versus dry batch, how long does that process take? Plus how long it takes to discharge. And in this example, it took 3 minutes, about 3 minutes for their standard design to come together to their ultimate workability, and it took another 3/4 of a minute to come out of the central batch into the truck. You run everything the same and you swap in this faster dispersing polymer, you can start to see where that performance impacts your operations. And it impacts, again, it reduces the mixing time it takes for your mix to become cohesive, and it has the potential to reduce your discharge time. And that starts to add up. And when you run the calculations, you can see that you now have the opportunity to essentially get more throughput out of your plants, out of your yard, and that translates into real dollars in savings. So it's connecting the advances in the technology to actual real-world type of applications. This is an example. This is an actual case study where we did establish real-time data. And for this operation, the only impact that fast dispersion had on the producer was in the mixing time. So we did not measure the discharge, any increases in discharge. So only considering the mixing time at this batch plant. This is an inventory precaster that chose 2 high volume mix designs to see what the impact is to their operations. The first design, they established what their baseline is with their standard PCE, and they ran many, many yards of this. Then they swapped in, changed nothing, simply swapped in the new faster dispersing PCE and measured how long it took them to batch this. Going from 3 minutes in this first example, going from 3 minutes to 2 minutes, essentially improve their production rates by 50%, which for them translates into some pretty big yardage, batches per day and yardage. They can, on an annual basis, they can improve their operations by 300 yards per day. That's pretty amazing. In the second case study where they changed designs, another one of their highly used designs, the majority of their products, it went from 2.6 to 2.26. So slightly less in terms of what the improvement is, but it still translates into a 15% increase in production. And again, that yields tangible dollars into a producer's pocket simply by leveraging faster dispersing PCE chemistry. So the takeaways here, while that was very fast, I wanted to leave a lot of time for questions. Even after 30 years of PCEs being commercially available, there are still opportunities to make improvements on the fundamental level to that chemistry. And those changes are yielding commercially viable improvements. The new PCE1 that I referred to, those faster dispersing polymers, allow for faster workability generation and lower sensitivity to changes in your cement. These new performance characteristics provide real value to a producer beyond just the improved performance that they're finding in the concrete. It impacts their operations in a positive way as well. And finally, the impact of faster workability generation enables these producers new efficiencies that they hadn't had in the past and yield increased profit for their operations. Any questions?
Any questions, Joe? Slump retention?
So, yeah, so, yes, overall work, so these were examples, and as you saw, some of the workability come down over time. That's in highly demanding designs, especially with higher alkali cements. We did see somewhat of a loss of workability quicker, potentially, over time. In other instances, we did not see that. So it's very, it's more dependent on the mix design and the application and your total polymer delivered.
Okay. The second question is, at what point, say in the ready mix industry, at what point did you introduce the batching cycle? Did you introduce them both at the same? Is it during the batching cycle, or is it after all materials have entered the truck that you introduced the admixture?
It was in both. So there were many trials that were run, and it was, what we tried to do was replicate the existing process. So if the existing process of a certain producer, ready mix, was to batch everything into the water and then hit it with the admixture, we did it that way so that the time comparison was identical. In other operations, we had it up front with the mixed water. So they had the water in, they added the admixture, and then the materials. And in both scenarios, directionally, the wet out characteristics were the same in terms of they were faster versus their traditional PCE that they used. So setting time, yes, there's no significant change in set time, so it's not accelerating the set of anything. The only acceleration is dispersibility, so you have rapid dispersion without rapid acceleration.
I was more so concerned about retardation.
Yeah, no, we are not seeing any retardation, any different. The setting characteristics and setting profile is the same as a general PCE.
And then I know you talked about mixing.
Mhm.
Did you do any studies with the effect of over-mixing with these dispersants and how that may affect the properties?
Off the top of my head, overmixing in terms of
So,
extended mixing?
yes.
So extended mixing is common practice for us to evaluate, and yes, the extended mixing had no negative impact beyond what you would see with a traditional PCE. There was no difference.
Thank you.
Question over here.
Have you checked if your new PC is sensitive to the presence of clay in the concrete?
Is it sensitive to clay is the question.
So is it sensitive? It's sensitive to clay like the rest of the PCE families are. So clay in particular, your swelling clays, it will still be impacted by the presence of a swelling clay, no more or no less than a traditional PCE.
Other questions? Right here.
In the experiments that you have conducted with different sulfate sources,
Different sulfate, no. So when you say different sulfate sources, what are you?
different types of gypsum, plaster,
So the sulfate available in the cement.
Yeah, so no, we chose sulfate, our sulfate analysis was done based on whatever that cement that we chose is. We did an internal quick pour solution test to quantify the sulfate that's there, and we just went with that to determine where we stand in terms of the sulfates, but no alternate types of sulfate.
Yes.
Any differences in air and pressure?
No, no. We tested it with both natural and synthetic air entrainers, and the impact was very similar in terms of not only the hardened properties of what that air entrainer combination with the PCE can produce, your mix design, how that dictated, it did not deviate from the standard reference, which was a standard PCE polymer.
Yes.
Is there a difference on the compressed stress?
Impact on compressive strength.
We saw improvements in the overall compressive strength, especially at early ages, and our hypothesis is that because of the increased efficiency of the dispersion itself, you have a better dispersed mix, which hydrates your cement more efficiently, providing you generally better compressive strengths at all ages.
Any other questions? Any questions? Yes, I have a question.
Yes.
I did raise my hand. On slide 6, you showed the 1 minute, 3 minute, and at 3 minutes there was a significant drop in workability. And so is that so a couple questions. It looks like that might not be an improvement in dosage efficiency overall for that combination. And then why do you think you get this wet and then a pretty quick stiffening with that combination?
So I really wish that Tom Vickers was here, since he actually ran all the experiments and could explain it better. But in theory, to explain the drop-off is workability, retention, and dispersion are essentially opposite ends of the spectrum. So I would interpret that as you have fast dispersion. You can't have both. If you're delivering highly efficient PCE binding, you have fast dispersion, you're consuming that, and it's not staying in the system long to maintain workability.
So as a follow-up, then does the fast wet out result in an overall reduction of mix time? Because here you would still need to mix 3 minutes to see what the final workability is? If you discharge that at 2 minutes, then what does that,
I'm sorry,
Does he
ask
follow?
that again.
so the total mix time,
Yep.
does the total mix time, even though you wet out faster, does the total mix time get reduced? Because here, at 3 minutes, you actually had less workability, so do you need to leave it in the mixer for the same length of time?
No, because you achieve your ultimate, you know what your ultimate workability is. If you're targeting an 8-inch slump, your general purpose PCE gets you there, I'm making this up for example's sake. Your general PCE gets you that 8-inch slump in 2 minutes. You know that that 8-inch slump is where you want to be. A faster dispersing polymer gets you there in 1 minute. You don't have to leave it in to see where that mix goes. You've already achieved it at 1 minute. Does that answer
It
your
makes
question?
sense. I'm just curious if you actually discharged it at that 1 minute, and let's say it went into a bucket at a precast plant.
Yep.
Would it then lose some of that based on this result? That's my question. really.
Yeah, no, we haven't seen, especially for a precast, because the mixing, they can reduce, the inventory precast case study is a good
Mhm.
example of that. So they are able to reduce their batch time without sacrificing the plastic performance. It doesn't go away fast in a sense that they can't get it placed into the forms effectively. They are still, it's not rapid slump loss.
Okay. Vartan, you have a question?
Oh, no.
Do you compare the type of transportation for the fast wetting mix, like bucket versus ready mix?
The more efficient, yes, the answer is yes. We did look at multiple mixing procedures. You know, the type of mixing dictates the ability to disperse, the effectiveness of that dispersion rate. So if,
Talking about transport, what I've seen is fast wetting mix, if you put in a bucket, it gels quicker than cold pieces.
I am not familiar with the gelling phenomena.
Or losing stuff when steady.
Yeah, we aren't seeing that rapid slump loss that you're discussing. Where we've seen that is more, if they're getting rapid slump loss, they're getting it from their general use PCE as well as their fast dispersing PCE. It's a mixed design and the components in there that are causing that rapid slump loss more so than the impact of which PCE they're using.
One more question right here.
How did you determine the dosage for your admixtures? If it was based off of slump, like if you look at the second curve over here,
Mhm.
your dosage at 3 minutes for PC2, what I'm assuming is the mix the kind that you run for that one. It's much less than the dosage for 1 minute. The slump is much less than the dosage for the PC1 at 1 minute. So how did you determine the optimal dosage for emphasizing?
The experiment. So they went in and they ran pre-trials to determine how do you achieve, what level is necessary to achieve that initial workability, and they calculated that out and then ran experiments based on that. So it
That
was,
initial workability based on 1 minute for PC1 and like 3 minutes for PC2, 3 minutes of mixing?
yes. So, yes.
Thank you.
Okay, thank you, Suzanne.